Everyone, and welcome to our next video. In this example, we're going to take a look at something called nodal analysis, and it is a different way to analyze a circuit. In this case, we're going to look at special nodes, and in this case here, node A is an important node, and we use the word essential node. So one of the things we have to do is identify what are the essential nodes in the circuit. So that node A, has current flowing in and flowing out. We also have a node at the bottom there, and if you notice, it's connected to both of the negative terminals of the battery. So when you have that, we are going to assign a reference node, and you can think of it as that is the node that will be 0 volts or ground. So first thing you have to do, identify essential nodes or node, and then assign a reference node. We're going to put in some other nodes here just to refer to them. We'll have node C and node D as well, because you're going to see how this method works. What we're going to do is we're going to focus on node A, because we have currents flowing in to that node and we have currents flowing out of that node. And what we do in nodal analysis is try to figure out information about those currents, and then we're going to use KCL. So we have this broken down like this here, so we just want to focus on these. Now notice we have a voltage source on the left. It is going to be pushing current from left to right. We have a voltage source on the right. It's going to be pushing current from right to left. Those are going to come into node A and logically move down through the load resistor and into ground. If I examine the current on the left, really to get that current, we take the voltage at node C, subtract the voltage at node A, and if you divide by R1, that would determine the current through that branch. On the other side, if you take the voltage at node D, subtract the voltage at node A, and divide by R2, that would be the current representing that section or that branch. Then we have the load current. Well, we can figure out the load current by taking VA, subtracting VB, which is really 0 volts, and dividing by the load resistor. So that is how you begin using nodal analysis. We basically look at node voltages and resistors to try to figure out the currents in each of the branches. So now that we have that, we can take a look at how we can piece all of this together. In some ways, using nodal analysis is easier than maybe Thevenin, but it does involve some algebra. We got to be careful with our algebra skills. We got to be careful with our signs and so on. But that's what nodal analysis involves. So we'll just relabel things here just so we remember what we have and the nodes that we're going to be looking at here. And then what we're going to do is we're going to write out an equation. So recall that we have that expression, VC minus VA, all over R1, that represents the current going in to node A from the left. The current coming in from the right is represented by VD, subtract VA, all over R2. Those are the two currents going in to node A. That's equal to the current exiting the node according to KCL, which is VA, subtract 0, which is really VB, and divide that by the load resistor. So there, we have an equation. And if you remember from algebra, this is a rational equation, and we need to solve this rational equation. We know what VC is. It's actually 32 volts. So I'm going to put that in. We know that R1 is 4 ohms. I don't know what VA is yet. I do know VD is 64 volts. And I know that R2 is 4 ohms. Over on the right-hand side, we have VA over the load, which is 8 ohms. So there, we have a rational equation which has one variable, and we need to solve for that variable VA in order to solve this problem. So, like I said, it's really at this point a test of your algebra skills, making sure you know how to solve rational equations. So if we just write things out again here, we're just copying what we had on that last page. And then we need to solve for this rational equation. You can see here that if we were to find a common denominator, it would be 8. So we want to get rid of those denominators because they're a little bit hard to work with. So I'm going to times every term by 2. And basically that will allow us to do a common denominator. Or I can simplify the left-hand side. So if we simplify the left-hand side, I've got 96 minus 2VA. So I just simplified the numerators on the left, put it all over 4, and now I will multiply both sides by 8. So that's going to give me 192 minus 4VA equals VA. Now, I just want to solve for VA at this point here. This is the simple equation. And we end up with VA is equal to 38.4 volts. So there, we know that node voltage. And really, that's the load voltage. So the load voltage is 38.4 volts. And if I wanted to find the load current, well, I know the load voltage. Just divide by the resistance of the load. So we end up with 4.8 amps. So that is finding the load current and the load voltage using nodal analysis.